All right, we're going to get started here with section 13.2, integrals of vector functions. Hopefully this will be very straightforward to you. We're just extending this idea of integrating scalar functions into vector functions, and it's actually pretty straightforward. So essentially here we have a definition of the indefinite integral of r with respect to t is the set of all antiderivatives of r, denoted by the integral of r of t dt. If r is any antiderivative of r, then this is the case. If we take the integral of little r, we're going to get the antiderivative of r plus some constant vector right there. Why exactly we have a constant, I can't even get the symbol on there, why exactly we have a constant vector there instead of just some constant will become clear in just a few minutes. So that's the basic idea, saying we can take an integral of a vector function, and it is just the antiderivative. So just like before, if we took the derivative of a vector function, we took the derivatives of each component individually. Well, we can do the same thing in reverse here. We can find the antiderivatives, or the integrals, of each component individually. So if we're doing the integral of this entire thing, we just have to do the integrals of each individual component, like that. And then what happens is you end up having to add a constant onto each one of these integrals. So that's that integral right there, plus some constant. This integral plus some constant. This is this integral plus some constant right there. So each one of them has a constant added onto its component. And then all we simply do with those constants is you can just pull them out. So it's the vector, you see it right here, C1i, C2j minus C3k, and it could be a plus C3k actually. I probably would prefer it if it had a plus there. And you just, and then this, I guess, would have to be a minus or something. But anyway, there's something there where we can just pull all three of those components out into their own vector here and just add a constant vector on the end that, of course, you have to remember has three components. Individual constants that go with each of your other components for the components that you took the integrals of. Okay, so you can pretty much just skip right here. You don't have to write this whole thing out every time and write this whole thing out every time. You'll probably just skip those two steps and just go ahead and just take the integral of each individual component and put plus a constant vector at the end. Okay. So here you go. This is just telling you another way to do it, but this time is for a definite integral. And again, you just split it up and do the definite integral of each one. This time you won't end up with that plus constant vector, because on definite integrals the constants cancel out. You end up with a plus the constant and minus the constant when you plug in your limits of integration, a and b, and so they cancel out. So you don't have the plus a constant over here. So you don't have that for the definite integrals. So let's take a look here, another example. This one's of doing a definite integral. Again, you can probably skip this step and just hop right on to this line right here, where we've done the integral of each one individually. The derivative of sine is cosine, so the integral of cosine is sine. This is just a 1. The integral of 1 is just t. The integral of 2t becomes just t squared, right? Add 1 to the exponent and divide by the new exponent. And then you plug in your limits of integration. So sine of 0 minus, or sine of pi minus sine of 0, pi minus 0, and then pi squared minus 0 squared. And then that works all out. You see this first component is going to go to 0, and you're left with pi j and minus pi squared k. And there is your integral of that vector function from 0 to pi. Okay, here I worked this out ahead of time, so you didn't have to sit here and watch me write all this out, but I'll walk through it now with you. Suppose we do not know the path of a hang glider, but only its acceleration vector. A as a function of time is equal to negative 3 cosine ti minus 3 sine tj plus 2k. We also know that initially at time t equals 0, the glider departed from the point 4, 0, 0 with a velocity v of t equals 0 equal to 3j. find the glider's position as a function of time. Hopefully you can recognize, well, maybe not at this point, but at some, maybe as you get a little more comfortable, you could even look at this acceleration and even realize what kind of a motion this is going to end up being. So let's go ahead and start with this part up here, where we are doing the, to get the velocity function, we need to do the integral of the acceleration function. And we need the acceleration function because to get the position function, we have to integrate the velocity function, okay? So in order to get position, we need to integrate velocity. In order to get the velocity, we have to integrate the acceleration. So that's what I'm going to go ahead here and do. I'm going to integrate both of them here to get this done. So let me get a different color here. Let's do blue, I guess. So I'm going to do the integral of my acceleration function. I actually wrote this all out. I did the individual ones, right? The integral of each individual one. I'm just kind of showing you this at the beginning, but normally you can skip that whole line and jump right to here where we get the velocity as a function of time. And the integral of negative cosine, or the integral of cosine is sine, so we end up with negative 3 sine t, and that's in the I direction. The integral of negative 3 sine, well, so it's the integral of negative sine, is just cosine, because the derivative of cosine is negative sine, so we end up with a positive 3 cosine here. And then over here we just have the integral of just dt, you know, we pull that constant out in front, and so we end up with just 2t from that one right there. And then, of course, at the end, you add on your constant vector, because this is an indefinite integral. Now we have to figure out what that constant vector is. So we use our initial condition that's given to us, that the velocity at time t equals 0 is 3 in the j direction. And so I plug that in. Velocity equal to velocity of time t equals 0, and then I just plug in zeros for each one of these. 0, 0, 0, and it has to equal that 3j from up here, right? So as I go through and plug that in, you know, you see things like the sine of 0, that whole thing is 0. The cosine of 0, that part right there is just a 1. And then 2 times 0, that whole thing is a 0. So everything became a 0 except the 3j, right? And since that is the case, I actually should have had, sorry, I missed this little part up here, hold on. We should have a plus the c vector. I realize I forgot to write that there. I did write it on the next line though. Plus our constant vector. Well, what we end up then, as we go to the next line, is we have that 3j, because the I component and the k component went to 0, plus c has to equal 3j. Well, what does that mean? That means that c has to be the 0 vector, because 3j is already 3j. So we get a therefore, the c vector is the 0 vector, and then therefore, again, this time, therefore, this up here, if we go back up this line, that is 0. And then I can just say this part right here, that is my velocity as a function of time vector equation right there. All right, and I should probably put little vector symbols on all these. Sorry, I didn't do that. Vector, 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 vector. And so we have to do the integral of the velocity function in order to get the position function. So here we can do this by just doing this integral, all right? So I went ahead and just skipped writing all that out because I was getting low on room there. But basically the integral of negative 3 sine t is 3 cosine t. And the integral of 3 cosine t is 3 sine t. And the integral of 2t is t squared. And then, of course, plus a constant vector. And so now we've got our position function almost totally done. We then have to just go back through and actually figure out what that constant vector is. To do that, we take this initial condition that was given to us up here, that the initial position is 4, 0, 0, and so I plug that in. So at time t equals 0, that's the initial position, I plug this in, 0, 0, 0 for everything in my position function, right? This was my position function. Plug in t equals 0 for all of it. Then I put my plus c and I set it equal to 4i, because that's what this would be. The initial position vector would be 4i plus 0, right? Plus 0j plus 0k. That's that 4, 0, 0 position initially. And then as I plug in 0, I get the cosine of 0. This is a 1. This whole thing is a 0. This whole thing is a 0. And so I end up with just 3i, right? That's from this right there, plus c1i, c2j, c3k. I went ahead and broke my my constant vector there, my constant c vector up into its components just to show this to you. Well, if we look, what it equals is just 4i. That means there can't be any j components or k components. So these must be 0. And then I just ask myself, 3i plus what I equals 4i? And the answer is 1, right? Or I could just subtract the 3i over, and you get c1i equals 1i. That means that c1, right? So like another therefore, c1 equals 1. Okay? And so what you can do is you can come back up here to this vector and change that c right there, that plus a constant, and just make it just an I, plus an I right there. Okay? And if you really, I guess you wanted, you could include that over, and the first component could have been 3 cosine t plus 1 in the I direction, but you can also leave that I off to the side. But if you wanted to combine over, you could take and combine it over with a plus 1 into there. Okay? I won't leave that on there to confuse you, but I don't have room to rewrite that whole thing out there like that. Okay? So then ultimately this, oops, not a very good, this is your position function. There you go, as a function of time right there. That's it. Okay? So go ahead and go back and, re-watch that one if you want to make sure you get it. So right here, we've got the path of a hang glider with position vector r of t. So this is missing the plus 1 right there. Well, actually, that's not the same one, is it? It's the same almost thing, but it's a different starting position. So I guess they decided not to worry about that plus 1. So anyway, I guess with the plus 1, it would have started out here at 4 instead of at 3, but they didn't do that. So it's almost the same thing, not quite the exact same one. But there you go. That's the path the hang glider would be doing. It would be, not spiraling, but going up in a helical path up into the air. Okay? So it must have hit like some sort of warm air patch right there that's helping to raise it up. I'm not sure if y'all knew that, but that is what people on gliders do. They'll look for a spot of warm air where the air is rising, and then they'll go in circles around it and let that air push them up higher so that they can go farther. So they fly along losing altitude, and then they find a warm spot and they use it to spiral themselves up, and then they fly along here and they find a warm spot and they use it to circle themselves up as much as they can, and then they start gliding back down. Birds also do this. If you ever see birds just with their wings out and they're just going around like that, and I think I said the word spiral, they're going helically around. It's not really a spiral. They're helically going around like that, and you can see a bird just doing that, going in circles, and they're gaining altitude with that little area of warm air. So after this, what we can talk about is another application of these vector functions, which is the ideal projectile motion equation. So this is where we don't have any wind resistance, and we're staying near to the Earth's surface such that the acceleration is a constant. What you have happening is when you launch something, you're launching it at some angle, and this angle will be alpha. And what you find when you do this, if you ever taken a physics class, is that the orthogonal components here, the x direction, the horizontal direction, and the vertical direction, are totally independent of each other. And so if we have some initial velocity v naught that we launched it at, our initial horizontal is v naught cosine alpha, right? That's that component of it. And then the vertical one is v naught sine alpha. Those are our initial components of our velocity vectors. Now, what is also done here is, excuse me, this is for position, is those are velocities, and so you integrate them with respect to time, and you add on that time right there, right? When you integrate v naught cosine alpha with respect to time, you get v naught cosine alpha times time. And same thing over here, we end up with it times the time. So this right here, this is initial horizontal velocity, and this right here, or not even just initial, it's a function of time. Well, that little part in there is without the t. Yeah, so not counting the t, just this part. This is initial vertical velocity, okay? And then you add the time onto it, and we can, move it through time. This extra little part on here vertically, we have this vertically, we don't have it horizontally. That's because gravity pulls things straight down. And therefore, we have an acceleration downward, right? We have a vertical acceleration, but there's no horizontal acceleration. So there's nothing here in this component to worry about for acceleration, but this little part right here accounts for the acceleration vertically. I won't get too crazy into where that comes from, but it's a constant acceleration. Actually, I might as well. It's constant acceleration, a equals that. And if you integrate it the first time, right, you integrate these with respect to time, you get the velocity function, and then that's going to equal gt, and they even add this negative, but usually the negative's inside there, but it's a downward acceleration. We put that on there, and then you integrate it again with respect to time, and you get gt integrated as negative 1/2 gt squared. So that's just the idea that our position, at least the positions being affected by the acceleration, is affected by negative 1/2 gt squared by doing that integral twice. Okay, so if you need to see that again, just come back. I don't want to leave that mess on there. So that's this is the accelerations part. Okay, this is due to downward constant acceleration. Okay, so that's downward constant acceleration. So projectile motion describes how an object fired at some angle from an initial position and acted upon by only the force of gravity, so no air resistance, moves in a vertical coordinate plane. Essentially, the shape that you will end up with here is going to be a parabola, according to these equations. It's an inverted parabola, all right? In reality, it's not quite a parabola. There's a little more to it than this, but it's extremely close to a parabola. All right, the components of R give the parametric equations x equals this. So again, this is the horizontal. This is the horizontal position after a time t, and this is the vertical position after a certain time t. X is the distance downrange, and y is the height. So vertical position and horizontal position, and they are totally independent of each other, except for time, because once vertically it hits the ground or horizontally it hits the ground, the timing stops. That's the big connection between the two, is that however long it has to travel vertically is also how long it has to travel horizontally. Okay, so you can see here they're breaking the components down as I just did for that previous picture for the initial launch. And then over here, you always have your velocity vector that's tangent to your projectile path, and the acceleration is always pointed straight down. Okay? And then if you wanted to find the velocity anytime, you just take the derivative of the previous one and take the magnitudes here. So here's an example. A projectile is fired from the origin over horizontal ground at an initial speed of 500 meters per second and a launch angle of 60 degrees. Where will the projectile be 10 seconds later? So here you can just use this equation. You can plug in the numbers that you have and find the components of it. And this is the components of its position after 10 seconds, where we plugged in the 10 seconds. This was 10 squared right there, okay? And when you do that, it gives you that. And so 10 seconds after firing, that's where its location will be. It will have moved this far horizontally, and it'd be this height vertically, okay? But it doesn't tell you something like whether or not it's still on its way up or on its way back down. So you're firing it, and it could be, you know, it 2 times it should be at that 3,840 height on its way up and on its way down. So this what we did right here doesn't tell us which one that happens to be, whether or not this is at 2,500 or this is at the 2,500. We don't really know in this situation. Okay. So, but at 2 places it'd have that same height. So let's take a look here. How do we find the maximum height? So you can memorize that right there, or get used to using it, or you can basically look and say, all right, when this thing goes up and comes back down, remember the velocity vector is always tangent to our line here. And so at the highest point, the velocity vector is purely horizontal. There is no vertical component to it. So this happens when the vertical component of the velocity equals 0. Okay? The y component, or the vertical component, equals 0. Flight time, you get this by figuring out how long it is in the air, right? How long will it be according to this part right here? How long is it actually in the air till it hits the ground? Sometimes you might have to come over here and use it, but remember the times are always the same. So you figure out, according to this, how long is it till it gets to 0 height, or whatever height we're trying to get to. After you know that time, you can plug it in over here and see how far would it have traveled horizontally in that amount of time. Okay, and so they've gone ahead and done that all for you and put that together for you, combining those 2 ideas of when you get back to 0 time. So I'm assuming this assumes when you get to S vertical equals 0, okay, and then combine those 2 things together to figure out, how long it was in the air. So well, I guess you don't need that. You just need S vertical equals 0, and you can use either one of those 2 components to get that. And then to find how far it actually goes down range, you take this time up here that you got, this time right here, and you plug that into the horizontal component and see how far it could have gone. So S horizontal at this T right here, this T right there, okay, as a function of that time. You plug that time back in to the horizontal part, and then that gives you the range of how far it can go in that time. Because if it's in the air for 3 seconds, that means it has 3 seconds to travel at its horizontal speed before it hits the ground. All right, because if it's, after it hits the ground, we're not worrying about it rolling or bouncing or anything else anymore. We're going to pretend it just hits and sticks there. All right, here you can see another picture of the path of a projectile. This time it's fired not from the ground, but from some other height, x naught, y naught, and it has an initial velocity v naught at an angle of alpha degrees with the horizontal. And then here is an example. A baseball is thrown from the stands 32 feet above the field at an angle of 30 degrees up from the horizontal. When and how far will the ball strike the ground if its initial speed is 32 feet per second? So I'm going to leave this one for you to try. They give you the position function right there, the vector function right there. See if you can figure this out. You're not starting at the ground, you're starting 32 feet above it. So see if you can figure this out. I'll work it out. You can take a look in the notes, and you'll be able to see it there. If you need to, it'll be worked out in the notes, okay? And I'm pretty sure that's the extra page, yep, to work it out on. And that's pretty much it for now. So thanks for listening, and we'll see you next time.